So previously we have looked at topological invariants of X. Now we want to look at the analytic invariant. So one way of exploring the viewpoint that X is a complex manifold is by studying the sheaf of differential forms. And we can explore that in two ways. So one way is by looking at the sheaf cohomology of it. Another direction is to exploit the fact that the square of this sheaf is an invertible sheaf. And invertible sheaves can be thought of as line bundles or divisor. So we could explore that direction. But for now, we will look at the cohomology of this sheaf. So from that viewpoint, we get the invariants called the Hodge numbers. They are defined to be the dimension of the cohomology groups of powers of these sheaves of differential forms. Note that by definition, the zeroth power of omega x is just defined to be the sheaf of holomorphic functions on X. Thus, for every surface, we have a Hodge diamond like this. Now, these four numbers are actually equal. We call these the irregularity of the surface. And then we also have these two numbers are actually equal, and we call them the geometric genus of the surface. We can also define the arithmetic genus in this way. Note that some books put this 1 over here so that this is an alternating sum, h20 minus h10 plus h00. But using our definition here, we see that the irregularity is just a discrepancy between the geometric and the arithmetic genus. So why is this called irregularity? Well, this is a historical reason. So for the first surfaces that were studied, so these are the non-singular hypersurfaces in P3 and also the rational surfaces, then this irregularity actually vanished. And so people presume that's the regular phenomenon, that's a common phenomenon. So they call surfaces for which this quantity vanished regular surfaces. For example, all rational surfaces are regular. Is the converse true? Is it true that all rational surfaces must be regular? Well, it turns out not to be true. For example, Enrique surfaces have zero irregularity, so they are regular, but they are not rational. It turns out that to detect the rational surfaces, just using the irregularity is not sufficient. But if we add the condition that the second genus of the surface vanish, then being regular and having the second genus vanishes implies rational. So that's if and only if. So those two invariants, irregularity and the second genus, classify rational surfaces up to birationality uniquely. Next, we want to explain how these three different quantities are actually all generalization of genus in the case of curves. But before that, let us explain how these Hodge numbers relate to our previous invariants, the Betti numbers. So we have the following relationship. The mth Betti number is going to be the sum of the Hodge numbers whose indices add up to m. So in particular, from here, we see that the irregularity is just 1/2 of B1. So a surface is regular if and only if its Betti number B1 vanishes. Alright, so now let's discuss the name. So for curves, we only have one notion of genus, but for surfaces, we have two notions, right? So how do these notions, geometric genus and arithmetic genus, generalize the concept of genus for a curve? So let's look first at the definition of geometric genus. Actually, we can define this not just for algebraic surface, but for any complex manifold, algebraic complex manifold of dimension n. So let's say we have a complex manifold of dimension n, then this geometric genus can be defined to be the dimension of the global section of a line bundle. Which line bundle? Well, to get a line bundle from the cotangent sheaf, we need to times itself n time, so this. And note that in the case of curves, this is just gonna be the genus. This is by Riemann-Roch and Serre duality. Look, this is the Hodge diamond for a curve. So the geometric genus is a generalization of the curve genus in the sense that we're replacing this 1 by the maximum dimension. It's the dimension of the complex manifold. Now, let's have a look at the arithmetic genus. Similar to the case of geometric genus, this is a definition that also generalizes for a complex manifold of any dimension. It will just be defined to be these alternating sums of dimensional cohomology groups of OX. Now let's see what happened in the case when the dimension n is 1. When the dimension n is 1, this is just H10. And as we see here, that is the usual genus. So the arithmetic genus is again a generalization of the usual genus. And finally, as we have mentioned, the irregularity that comes from the discrepancy between the arithmetic and geometric genus, and it's 0 when in the case, but it's not an if and only if, when the surface is rational. So those are the important invariants coming from the Hodge numbers of a complex manifold. Next, we'll look at two more invariants, the canonical class and the n genus.